The last thing we should think about is actually what the intensity of our fringes are. Now, the book does mention a few things in here that might not be familiar to you because we did skip a chapter that we're about to go back to. So thinking about how the intensity here actually relates to the magnitude of the electric field is something that we haven't talked about. But the main takeaway here doesn't depend on understanding that. So there's an equation that the book derives which says that our intensity for the double slit experiment depends on this. Notice that this is a function of y, which is measured from this center point here. So going up and down, we get this cosine squared dependence. Remember that it should make sense that this is cosine squared because we can't get a negative intensity. Intensity starts at 0 and goes up. So then we have this, this intensity depends both on the spacing here, remember that's d, and it depends on L. So the intensity actually depends on both d and L and the wavelength, but that's inside the cosine squared. So that just tells you kind of what spacing these have. Then we look at the coefficient out front, and it's 4I1. Now I1 is the intensity you would get from one slit. Now what's a little bit tricky to think about is that if I have one slit, you would kind of expect this to just illuminate this evenly. Now we're going to find out that that's not quite the case. But if we just said that I let my light shine through one slit, we would get the intensity I1. So what's interesting here is that we have 4 times that. Not 2 and not 1, but 4. And one of the ways you can think about this is that, well, there's 2 slits. So it's like you get I1 from one of them, you get I2 from the other. You would still maybe think that that would give you 2I1. And what's interesting here is that's what your average is. So if we didn't have any interference, if we just had an even illumination, that would in fact be 2I1. But sometimes you have constructive interference and sometimes you have destructive interference. So your destructive interference goes to 0 and your constructive interference goes to 4. And what the book points out is that we haven't changed the amount of energy or the amount of light coming through. We've just kind of moved where it is. So instead of it being 2I1 evenly everywhere, it still averages out to be 2I1, but some places are 0 and some places have a maximum value of 4. So this is just kind of to give you an overall view of what's happening, that effectively, if you want to think about light as energy, conservation of energy still holds, but diffraction and interference is giving us this interesting pattern that it ends up in a different location. Now there's one correction that it's time to talk about, and that is the fact that this intensity isn't actually even. So our central maximum is the brightest, and as you get further away, our fringes get dimmer and dimmer. Now this is actually due to the diffraction through a single slit, and we will talk about this in a later section of the book. So if we want to call this basically the envelope. This envelope is due to diffraction of a single slit. The fact that you have these kind of fast oscillations is due to 2 slits. So as long as your individual slits are really narrow, you can pretty much ignore this single slit diffraction effect. But if you have pretty wide slits here, then this can become more noticeable. And where that's relevant is if you go to actually do an experiment, it's hard to make these slits really, really thin. So in experiments, you definitely see this, but when we think about it in the book, well, we can make any book problem we want, and so it's easier to have an ideal system where our slits are really, really skinny, and we don't have to worry about how we would actually construct that. So what you'll actually observe if you go to do this experiment is that they are varying in brightness, but that isn't due to any aspect of the double slit experiment, not at least how we've derived it, but it just has to do with the finite width of an individual slit. The wider you make each slit, the more you see this and the faster it falls off. So once we talk about single slit diffraction, this might make a little more sense. The book goes through a full derivation, including both the single slit interference, two slit interference and single slit diffraction. The book does a whole derivation. That's section 5, and I'm going to skip that, since typically we can think about one regime or the other. One of these effects is usually much more dominant than the other.